contributed by Chang Ma on supermassive black holes. So
Is that on? Okay, good. Now that Raphael's given away all of my secrets, well, I guess I'll just have to give the colloquium anyway. So I'm grateful for the support from the Institute for Advanced Study. And also, I'm proud of my collaborators here at Berkeley. So I thought I'd put up their faces here because everyone involved in the papers that I'm going to be telling you about, except me, is actually here right now. So if for some reason you're scared to interrogate me or I'm gone, as I leave at the end of this week, you can find anybody who looks like one of these people and start asking them questions. So what I'm going to tell you about depends in an important way on background in general relativity. I thought I'd just give a brief refresher before getting into things. We have a notation that involves objects called tensors that are used to easily ensure that all quantities that are statements are invariant under coordinate transformation. The basic field is a metric, which is a 4x4 symmetric matrix. And you can construct various things out of it. The most important thing maybe being the curvature tensor, which is a sort of a two derivatives of the metric that says how space and time are curved at a given point. And by contracting indices with the metric, you can also construct a Ricci tensor that has just two vector indices and a scalar. Now, the important thing here is that you can, now we talk about the curvature of space-time, the fundamental equation of general relativity says that part of the curvature of space-time at a given point is determined by the properties of matter, the stress-energy tensor of the matter fields at that point. So what is the stress-energy tensor? Well, like the metric, it is also a 4x4 symmetric matrix. So you can write it out. If you have Minkowski-like coordinates at a given point, you have time and 3 space directions, then because it's symmetric, there will be 10 independent components of this matrix. And they each have their own interpretation from the perspective of somebody in a given frame of reference. The time-time component also goes by the name of energy density, the rate at which energy is flowing through time, because energy is momentum in the time direction. Then the off-diagonal terms, because it's symmetric, you can actually interpret in two different ways. You can think of it either as the density of the x, y, or z momentum, the components, or you can think of it as the flux, the flow of energy along the x, y, or z direction. But then you can also think about the flow of the space momentum in a space direction. The diagonal terms of this matrix have a name that you've probably heard, which is pressure. And if they're negatives, then we call it tension. So, and this whole 3x3 matrix together, including the off-diagonal terms, is the stress. And in order to get a relativistic entity that treats time and space on equal footing, we need the whole matrix, and therefore it's called the stress-energy tensor. And we don't call it the stress, energy, momentum, pressure, tension matrix, because that would be too long. Now, one special case of this that's particularly worth thinking about is called perfect fluids. So a perfect fluid is a special sort of idealized matter where the stress-energy tensor depends only on two numbers. In a particular frame of reference, that's the rest frame of this fluid, there's the energy density, which is the time-time component, and then there's just the pressure, which is these diagonal terms. Now, and if you know the so-called equation of state of the fluid, you can also work out how the pressure depends on the energy density. Of course, this is only true in the frame of reference of the particular fluid. If you have a fluid that's traveling at a velocity, you would need to do a transformation, and you'd end up with some off-diagonal terms here. So why is this important? Well, you remember I was telling you about Einstein's equation that the stress-energy tensor determines the curvature. So we might now want to ask the question, what kinds of spacetimes are allowed? What is physically acceptable to appear, and what cannot happen? What's impossible? And now we come to this interesting fact, which is if the stress-energy tensor doesn't have any restrictions, then Einstein's equation doesn't actually have any content, because you could just write down any metric you like, just invent something with whatever sick imagination you have, and just solve for the stress-energy tensor, and that will be a solution to Einstein's equation. So whatever science fiction possibilities you might want to dream about, for example, maybe you want to take a picnic in the Andromeda galaxy, and you want to take a shortcut through a traversable wormhole and get there right away. Well, you can write down a metric of general relativity that has that property and is supported by some stress-energy tensor configuration in the middle. Or if you don't like non-trivial topology, you could instead make a warp drive space-time where the space-time squishes, it contracts in front of your spaceship, and it stretches out behind your spaceship, so that the net effect is that from the perspective of somebody sort of watching you from the outside, you're going faster than light. Now, it's important to emphasize here that locally, with respect to the metric near where you aren't traveling faster than light. You're just an ordinary object made of ordinary matter going slower than the speed of light. But the sort of net effect of this contraction and expansion is to carry you along faster than the speed of light relative to somebody looking at you from the side. And the worst of all, at least in terms of the amount of head scratching you have to do to figure out what it would even mean and whether it makes sense logically, if it were actually possible, is time machines. So technically, these go by a special name in the general relativity community. They go by the name of a closed time-like curve. So if you start at a given point of space-time, you could take a particular trajectory, taking a time-like path, go through some strong gravitational region, and maybe you come back to the original space-time point you started with. Not the same space at a later time, we can all do that, but the same space and time, and then you kill yourself or something and we don't know what happens. So the question is, are these crazy types of scenarios actually possible? Because once you throw open the door of curved space-time, a priori, you don't know what is or is not possible. Maybe these things are. But the considered answer of what is going on is that probably these things are not possible. Now, this is actually involves multiple steps. It's a little bit like that joke that maybe you've heard about a man falls out of the airplane. Fortunately, he has a parachute. Unfortunately, the parachute won't open. Fortunately, there's a haystack underneath him. Unfortunately, there's a pitchfork in the haystack. Fortunately, he misses the pitchfork. Unfortunately, he misses the haystack. So there's a sort of same fortunately, unfortunately structure in some of these physics arguments, where first there's a reason why it's impossible, and then there's a loophole in that reason, and then there's a reason why it doesn't actually work, and so on for several stages. So in order to explain this, I have to start at the top level of the joke with the parachute. And the first statement is that all of these things would require some sort of exotic matter that violates some sort of energy condition, like has negative energy or something, that normally you would expect reasonable field theories to obey. Now, when I say it's not possible, this is sort of an inconsistency, because on Wednesday I'm going to be telling you about a loophole that allows traversable wormholes after all. I don't have time to talk about that now. I'm just going to tell you that actually it doesn't violate causality at the end of the day. And if you're curious about the details, you'll have to come to the string theory group meeting on Wednesday. So energy conditions are the first level of things that makes these kinds of science fiction entities, unfortunately, not possible. So in what follows, K represents a null vector. That means a vector pointing in space-time at the speed of light that goes on the light cone. And T and U will represent time-like vectors that point to the future of the light cone inside of it. Now, there are a number of different energy conditions that people use in general relativity. So I've just listed some of the more interesting ones here. My favorite is the null energy condition. And here I've written down the thing that cannot be negative if the null energy condition is true. You take the stress energy tensor and you take a light-light component and you take the same light-light component for both of these indices. And that thing is required to be non-negative. Now, in the special case of a perfect fluid, just to build some intuition for what these things actually mean about ordinary matter, I've written out what it means in terms of rho and p. Of course, it's important to emphasize these energy conditions could be defined even for a not perfect fluid. For other sorts of matter, it's just an example. So in this case, you can see that the null energy condition places limits on the energy density, and it says there can't be too much tension compared to the energy density, for example. And the reason why this energy condition is interesting is that once you turn on gravity, it tells you that light rays, which go along what's called null surfaces, are focusing. More on that later. A slightly stronger energy condition is called the weak energy condition, and this one is probably the first thing that you would think of if you didn't know anything about energy conditions and general relativity and somebody just asked you to write down what seemed like a reasonable assumption for a stress energy tensor. You'd probably say, well, the energy density, that had better be positive instead of negative, because things have positive mass, not negative mass. And oh, by the way, that had better be true in every frame of reference. That would give you the weak energy condition. And it tells you that in addition to the null energy condition, for a perfect fluid, you would need, of course, rho to be positive. You have positive energy in every frame. A classic example of a situation where you violate the weak energy condition, but you preserve the null energy condition is if Einstein's cosmological constant is negative, which involves the geometry of something called the anti-de Sitter space. As a matter of fact, the cosmological constant is positive, though. So that doesn't apply to the real world. Then there's another energy condition that's called the dominant energy condition, where you say that these time-like vectors could be different from each other. And this one says, in addition to not allowing too much tension relative to rho, you can't allow too much pressure either. So there's a limit on both sides. And at some level, some hand-waving level, this is equivalent to the statement that energy can't go faster than light. Now, we all know information can't travel faster than light, but this is actually a different statement, that energy can't go faster than light. And the way to see that that's what this means is you just consider one of these time-like vectors here contracted with the stress tensor tells you they're choosing to think about the flow of energy. The time represents the time momentum, so that's energy. And then this thing is now a 4 vector. And that 4 vector that represents the flow of energy, we are requiring it to travel slower than the speed of light. And that is enforced by saying that its dot product with any other time-like vector should have the same sign. And there is another energy condition called the strong energy condition that is important, which has this rather strange combination of stress energy tensors that you probably would not write down if you were just writing something down that looked nice. But the reason why people think about this is that if you apply the Einstein's equation, it is equivalent to talking about the time-time component of the curvature tensor. And it tells you that if you have things traveling nearby the time-like direction, that these guys are going to focus. Now, there's a strange misnomer here in that you might have thought that the strong energy condition would imply the weak energy condition, but it doesn't. It's just what they're called. However, there is some precedent for this in physics because it turns out the strong force doesn't imply the weak force either. So it's not completely unprecedented. Now, The strong energy condition is actually a little bit defunct at the moment because you can actually violate it even for, well, it's satisfied for things like Maxwell's equations or the Dirac equation. It can actually be violated by things as simple as a scalar field with some potential, as for example, in inflation in the early universe. So most people think the strong energy condition is not actually likely to be valid in early universe cosmology, but still an interesting foil to compare models with. Now, all of these conditions actually end up being violated by quantum fields. So that is going to be, the next stage of this parachute joke is how do we deal with quantum fields. First, though, I want to tell you some of the theorems that you can actually prove using energy conditions, because you normally need to assume an energy condition to prove something in general relativity that restricts the space-time. So I said my favorite was the null energy condition, and the reason why it's my favorite is that you can prove so many interesting, physically interesting things just from this. For example, there's a theorem called topological censorship that says you can't have any traversable wormholes, that anytime you have non-trivial topology, it would have to be behind a black hole event horizon, and you can't actually get through it and see the other side. There are also theorems using the null energy condition which say that there are no warp drives. Now, it's actually a little bit hard to define what you mean by a warp drive in general relativity, because you have to make sure to phrase everything in a coordinate invariant way. And so when you say fast, what does it mean to travel faster than the speed of light? Compared to what? Since you're not traveling faster than the speed of light locally. But one way you can define this is in a space-time that is infinitely big, where you have a past infinity and a future infinity. You could just ask, do you go from past infinity to future infinity through some sort of warp drive faster than you would if you went around the long way? By that definition, it turns out you can also rule out warp drives. I should say, all of these theorems involve some technical auxiliary assumptions, things you assume besides the energy condition, about causality being reasonable or something in other respects. I'm just giving you the energy condition part of this theorem. Now, then there's also the time machines. There are some theorems that say, given the null energy condition, if you start with a space-time that doesn't have any time machines in it in the past, any closed time-like curves there, given certain assumptions, including the null energy condition, you can prove that there's no way to create a time machine. So this is a theorem that prevents you from creating causality violations. Although there's space-times like the Gödel rotating universe that have a time machine that have closed time-like curves at arbitrarily early times. And this theorem doesn't rule that out. And another interesting result is a sort of positive energy theorem that says, given the null energy condition, you can't have any negative mass objects. This is actually a special case in some ways of the no warp drive result, because in general relativity, there's an effect called the Shapiro delay, which says anytime you send light past some massive object like a star, the light is slowed down relative to what it would be if there was no star. This is an important effect for observations in astrophysics. But if you actually had a negative mass star, then instead of having a Shapiro delay, you would have a Shapiro advance. The light that went close to the negative energy star would get to you faster. So technically, it would actually be an example of a warp drive. And so not surprisingly, there's theorems that also rule this out, given the null energy condition. Now, I said isolated objects here because there's a bit of a loophole in this result, which is the result actually assumes that space-time looks for example, asymptotically like Minkowski space, not only as you go out to infinity in a space-like direction, but also as you go out to infinity traveling at the speed of light in a null direction. What that means is if you have one of those false vacuum solution that some cosmologists think about, where you tunneled into a lower energy ground state and you imagine a bubble of destruction coming out at the speed of light, destroying the universe as we know it and replacing it with something else that had negative energy, technically the theorem doesn't actually rule that out. So if you want to rule out that kind of ecological catastrophe, you actually need a stronger energy condition, which is called the dominant energy condition, which I also showed you on the previous slide. And there's various proofs using that dominant energy condition. Now, there's another seemingly pathological feature of spacetimes in general relativity that people often worry about. But here, actually, the energy conditions don't help us. They actually make things worse. And that's singularities. So in classical general relativity, there's a number of situations in which the theory predicts singularities, which are places where space-time comes to an end and it can't be extended any farther. I've drawn here a space-time cartoon of a collapsing star at the end of its life, which is massive enough to form a black hole. As the matter collapses, it eventually produces a singularity. So time goes up in this diagram. There is an event horizon that forms with the surface of the black hole, where if you fall across the event horizon, there's no way to ever get out again. In fact, once you're inside the event horizon, falling in towards the center is like falling towards the future in everyday life. It's completely inevitable. So when you cross the horizon, you'll necessarily fall in towards the center. Where there is a singularity, you get crunched to zero size, and time ends, so far as we know. Similarly, there's also a Big Bang singularity at the beginning of time in many models of cosmology. So it used to be people thought maybe these singularities were an artifact of looking at highly symmetric solutions. And if you actually solved using realistic generic initial data, you would not find any singularities. But people like Penrose and Hawking proved some singularity theorems that show that singularities actually form given some generic initial conditions. So I'm going to tell you about that now. There's actually two main singularity theorems that are different in their assumptions and their conclusions. The first one, the original Penrose singularity theorem, is based on thinking about how light rays focus into a singularity in certain gravitational situations, such as black holes. Because this singularity theorem is about light rays, it uses the null energy condition. But Stephen Hawking used the same theorem. He basically just turned it around in time to argue that if you have, that in certain cases you also have to have a Big Bang singularity at the beginning of time. But that only applies if the spatial geometry of our universe is flat or hyperbolic in geometry. If it's compact, like if it's a big hypersphere, this theorem does not actually apply. So in order to remedy that, Stephen Hawking proved a different singularity theorem. The Hawking singularity theorem applies to a closed universe, but it is about the focusing of time-like geodesics that go to the future. And this, therefore, uses the strong energy condition. Because it uses the strong energy condition, it is likely to be invalid during the period of inflation. There's also something else that sometimes is called a singularity theorem, called the Born-Guth-Vilenkin theorem, which tells you that if you have eternal inflation, where the accelerating expansion of the universe at the beginning of time expands forever, it can only actually be eternal to the future. It can't actually be eternal to the past. So the so-called eternal inflation, time would still have to have a beginning, or at least you'd have to go back to an earlier era of time where the universe is not expanding on average. This theorem, however, is actually very different from the other singularity theorems in that it doesn't assume any kind of energy condition. It's actually just a purely geometrical tautology about any possible geometries. So I don't actually consider it a singularity theorem in the usual sense. So for my money, the most physically relevant of the singularity theorems is this Penrose singularity theorem, because aside from quantum effects, it's the one that seems most likely to be valid in the real universe. So we want to start correcting with quantum effects. We want to start on this baseline. Now, all of these theorems involve technical assumptions. I've decided to ease my guilt a little bit by actually providing the technical assumptions for just one of these theorems, and that is the Penrose singularity theorem, or at least a taste of the technical assumptions. This is a theorem of general relativity. It's about classical space-times, and it has three main assumptions. The first assumption, which we've already talked about, is the null energy condition. But the second assumption, and this is pretty typical for proofs like this, is an assumption about the causal structure of space-time. This assumption is called global hyperbolicity because it is essentially what you would want to assume in order to evolve a wave equation consistently in the space-time such that there's a well-defined Cauchy evolution problem where you can specify the data at one moment of time and deterministically work out what the data is at any other moment of time. Basically involves two assumptions about the geometry. One is that there are no closed time-like or light-like curves, so that you don't have any causality violations. The second assumption is, roughly speaking, that there are no holes in space-time that information can come in and out of. The third assumption is that space is infinitely big. Technically, that it's non-compact, if you like topology lingo. The theorem says that if something called a trapped surface forms, then a singularity is inevitable. So what is a trapped surface? So if space-time is d-dimensional, let's just assume for the moment that d is 4, then you look for a two-dimensional surface with the property that if you shoot out light rays from that surface in the outward direction, the area is always going to be contracting. It's going to be decreasing instead of expanding. Now, this may seem very strange because normally, if you go outwards from some surface, you expect the area to increase. But you could imagine that in a sufficiently highly curved region of space-time where there is enough distortion of the geometry due to gravity, maybe the area would be contracting everywhere instead of expanding. You might wonder, by the way, what I mean by the outside if this space-time actually has some bizarre topology. By the outside, I actually mean whichever direction space is non-compact in. If you have something like a wormhole where space goes in several directions is non-compact, then that just means maybe both sides are the outside, and it will be very easy to find a trapped surface. So the key step that is behind this theorem and several of the other theorems is that the light rays focus. So the basic idea is you shoot out light rays from this trapped surface. And the attractive gravity means the light rays can only focus towards each other. They cannot defocus away from each other. So to define things a little more technically, you can define a null coordinate to parameterize each of these light rays with a value of b that maybe starts out at 0 and increases. And this is called an affine. We want it to be what's called an affine parameter, which is like the analog of proper time in general relativity. It is a sort of uniform parameter along the light-like direction. It's called affine because if you're going in the light direction, you can multiply it by any, you can multiply it or add any number you like to it, and it's still an equally good affine parameter. Then you can define the rate of change of the area with respect to this affine parameter. And if you take the rate of change of the logarithmic rate of change of an infinitesimal piece of area here, then this gives you something called the expansion. It's just a measure of how much the area is increasing as we move out. You can also define something called the shear, which in higher dimensions than the slide I'm showing you would say how a circle here would deform into an ellipsoid as you move up this way. So not everything here is important, but what's important is that there's actually a formula now for the rate of change of the expansion with respect to this affine coordinate. This is something related to the second derivative of the area. So this is a geometrical fact called the Ricciarduri equation that's true in any geometry, that you can relate this second derivative of the area to, oh, there's a minus sign missing here. So see that? There's a minus sign right where that laser point, where my laser pointer was. These guys are negative because they're minus something squared. This guy is the curvature tensor, the null-null component of the curvature. And if you assume the Einstein equation is true, you can relate this to the null-null component of the stress tensor. And if you then assume the null energy condition, then this thing is positive, which means this whole right-hand side is negative. So given that, you can then conclude that actually before a finite value of this v coordinate, theta actually will actually go to minus infinity. Because if theta is negative, this thing has to be decreasing because it's minus. And because there's a minus theta squared term here, it actually has to reach minus infinity in a finite amount of time. So that tells you that focusing implies that this null surface is going to come to some kind of end. But what kind of end? There's actually several things that can happen here. You can focus light rays just by, using glasses or something, and that doesn't imply the existence of a singularity. Because, of course, light rays can just cross each other. But it turns out, if we classify the things that can happen, if the light rays can cross each other, the nearby light rays can cross each other, or non-adjacent ones can also intersect and cross each other. These guys will result in these light rays sort of exiting this null surface. So the third possibility is that the light ray is not extendable and it hits a singularity. So it turns out that if space is an infinite, it's not actually topologically possible for all of these light rays to simultaneously all around the surface cross each other and disappear. Because if it did, then this green surface would actually be a sort of finite-sized time slice, a finite-sized slice of space at one time. And we've assumed that space at one time is actually infinitely big. This is a contradiction given the assumption of global hyperbolicity I told you about, which turns out to imply, as an implication, that space cannot change its topology. So if it starts as a non-compact space-time, it cannot become compact. So it doesn't really matter whether you've gotten all of the details of this. The important point is that there's a topological argument that says at least one of these light rays can't just do something innocuous. Instead, it has to actually hit an edge of space-time. And if it hits an edge, it's inextendable. It can't be extended any further. And if you're so clever as to have defined the singularity as a place where a light ray becomes inextendable, then you've just proven the existence of singularities. The other geometric proofs that I didn't go into the details of also involve this assumption of light rays focusing. So if you have positive energy, that will tend to focus light rays. If you have negative energy, that will tend to defocus light rays. If you ignore the non-linear terms in the Ricciardour equation that I had on the previous slide, this will just relate the second derivative of the area to this null component of the stress tensor. So we just care about whether this thing is positive or negative. But it turns out that in general, as I've been ominously warning you this whole time, when you start taking into account quantum effects, there can be negative energy fluxes. In fact, every single energy condition can be violated in quantum field theory in certain places for certain states. Although in general, this negative energy has to be balanced by positive energy somewhere else so that the total energy of the space-time is still positive taken as a whole. There's various papers about this. Here are 3 examples of situations where negative energy comes up. One famous one is the Casimir effect, where you have 2 parallel conducting plates, and you have a different quantum vacuum in between the parallel plates, and it turns out that it actually has negative energy relative to the normal quantum vacuum. So this has been, of course, experimentally measured in the lab as a small attractive force between the 2 conducting plates. Another situation is you can just have moving mirrors that if you just have something that reflects quantum fields off of them and you start accelerating the mirror, then the rate of change of the acceleration makes it emit pulses of positive or negative energy. And if the mirror starts suddenly accelerating towards you, that's the sign where it will emit negative energy at you. Or even something as simple as squeezed states that people make in the laboratory all the time. A squeezed state of light, so there's something called a coherent state that of light that is a state that saturates the Heisenberg uncertainty principle. It has the position and momentum degrees of freedom of the field are in sort of bell curves or Gaussians. A squeeze state still saturates the Heisenberg uncertainty principle. You just take the light and you stretch out one of the position degrees of freedom and you squish one of the momentum degrees of freedom of this electromagnetic wavefront in such a way that the Heisenberg uncertainty principle is still saturated. And when you make such states, it turns out that for certain parts of their wave cycle, the flux of energy is actually negative. So the question is, can we use these negative energy fluxes to actually circumvent all of these results and not only violate the singularity theorems, but also travel to the Andromeda galaxy and so on? Well, I think, unfortunately, the answer is probably no. And one reason I think this is because there's other principles of nature that can be proven with similar technology that can be extended to quantum situations. So another theorem by Stephen Hawking, it says that the total area of a black hole event horizon is always increasing with time. So when you feed a black hole with positive energy, it makes it grow. Just like when you feed people, it makes them grow. This is a classical result that also involves the null energy condition and focusing of light rays. In fact, the proof is very similar to the Penrose Singularity Theorem. But it turns out this statement can be generalized to quantum situations in a way that I'm about to tell you. And if this result can be generalized, why not the others? So an exciting result about black hole physics that was shown first by Jacob Bekenstein and Stephen Hawking is that black holes actually have a temperature, and they behave like thermal systems. So if you have a black hole sitting in empty space, it actually radiates Hawking radiation at a temperature that is inversely proportional to the radius of the black hole. So you can consider various thought experiments where you allow a black hole to radiate stuff, or you dump in a box of radiation. And what people discovered as they were thinking about this is that you can define an entropy of the black hole using the standard thermodynamic Clausius relation, which they misnamed the first law in this context. So we already know what the energy of a black hole is. That's just its mass by mass energy equivalence. And we know what the temperature of a black hole is. That's the temperature at which it radiates Hawking radiation. So by applying a standard thermodynamic formula, you can work out what its entropy should be, and you find out that it's proportional to the area of the event horizon, which is also the thing that grew classically. So this made people see that there was an interesting connection to the second law of thermodynamics here. This also applies to sort of generalizations of event horizons that appear in other settings. For example, in cosmology, there are horizons that appear in de Sitter space that also have these thermodynamic properties. Or there's something called Rindler horizons that appears even in flat, empty space when you have an accelerating observer in Minkowski space. All of these horizons seem to obey these laws of thermodynamics. One of these laws of thermodynamics is called the generalized second law. It's just the sort of generalization of the second law of thermodynamics that applies when you have a black hole or some other system with an event horizon. So you might think, I've drawn here a picture of space-time. Because the horizon is made out of, is a surface that moves out at the speed of light, I've drawn it at a 45-degree angle, like people do in relativity diagrams. And I've cut, this is a space at one time outside the horizon. So you can imagine, here's space at another time on the horizon, here's space at a third time. Information, seemingly, can fall into the black hole and be lost. So the outside of the horizon doesn't look like a closed system. It looks like an open system. Things can't get out, but they can get in. Nevertheless, there's a quantity you can define that seems to increase, just as if it were the entropy of a closed system where the entropy has to increase. But it involves a term that's proportional to the area of the black hole horizon. That's the entropy of the black hole itself. And then you also have to include a term that describes the entropy of any stuff that's outside the horizon. So for example, if you had a binary system where a black hole and a neutron star were orbiting, you of course have to include the entropy of the neutron star as well, and that would be in this S out term, the outside entropy. And the strange thing is, the sum of these two terms, as we go to the future, seems to always increase with time. This suggests that there's a generalization of the second law of thermodynamics to black holes, even though we don't really understand what the statistical mechanical underpinnings of this law are. We're sort of like we're stuck back in the 19th century where we have some effective laws of thermodynamics, and we're just beginning to try to get some clues about what the statistical mechanics, the atomic theory behind it is. My dissertation research, by the way, was essentially proving that this is true in a broader range of situations than had been proven before when you have rapidly evolving quantum fields falling across the event horizon. I did it just by thinking about quantum field theory on the horizon itself. Normally, you think about quantum field theory on a constant time slice, but it's also possible to think about quantum field theory on a slice of space-time that is at the speed of light. So I want to make this a little bit more precise now. There's this term I called the outside entropy term, but in general, we have to figure out what it means to talk about the entropy of a quantum field theory system outside of this black hole or other horizon. So if you take a Cauchy surface, which is our name for space at one time, so this is like a three-dimensional space, and you imagine a surface which divides it into two regions that we could arbitrarily call the interior and the exterior. We have some sort of state of quantum field theory having quanta or whatever of this space-time. Then you can define a quantity that's called the entanglement entropy. So the way this works is you take your quantum state, you restrict it to one side, say the exterior, and you now write a density matrix like you do when you have a partial system in quantum mechanics of the quantum fields on the side. Then the most interesting information theoretic quantity you can write down is the von Neumann entropy minus trace rho log rho of this density matrix. Now, if you started with a pure state, it doesn't actually matter which side you restrict to, you get the same answer. If you started with a mixed state, it does matter. Now, something happens here which is annoying, but sort of almost always happens in quantum field theory, which is that you have divergences. This quantity actually is infinite. And that arises because there are quantum field fluctuations that are very close to this surface, coming from the very short distance degrees of freedom that are entangled across this boundary. Fortunately, these divergences are local. They correspond to integrating certain geometrical quantities along this surface. So they're under good theoretical control, and you can sort of factor them out. But one thing that you can, a game you can play that's more sophisticated, which defines the generalized entropy that's used in the generalized second law. If your theory is gravitational, better plug in this thing. Should have done that from the beginning, I guess. All right, do you know where the plug is? Oh, here it is. Here it is. Just make sure that's working. All right. We're good to go. So if your theory is gravitational, then we actually want to define, for purposes of this generalized second law, a finite quantity, because black holes should have a finite amount of entropy. And we can do that by just taking what we did before. We take the area of the black hole, which, because it can now be slightly modified by quantum field, I've put an expectation value around it. And we add this entropy outside and some short list of counter terms that are local geometrical quantities. So in any quantum field theory, when you analyze the entanglement entropy at one of these surfaces, the leading order divergence is always scales like the area. This is an important fact in condensed matter systems as well. when you have this area law divergence, you could think of that as just shifting or renormalizing the value of 1 over g, and you absorb the infinity into that. Similarly, there can be subleading divergences that you absorb into some other integrals of quantities here. I don't want to go into the details of this, but any of you who are familiar with quantum field theory know that you frequently have to absorb infinities into local quantities in order to make it work. So once you've defined this generalized entropy precisely, this suggests a way of trying to extend all of these classical general relativity proofs to quantum situations. You can just replace the area with the generalized entropy. This gives you, so I defined before the expansion, that is the logarithmic rate of change of area per this null v coordinate. You can replace this with what we call the quantum expansion, where you just replace this area here with the generalized entropy, still per unit area. This is sort of like taking a functional derivative, because if you start with, if this sigma is your entangling surface, that's the equivalent of E in this previous picture, and you shoot out a null surface from it, you evaluate the density matrix on this state. Given this null surface, which now this is a face-on view that's composed of a bunch of light rays, so these light rays go up in the diagram, if you imagine like they're coming at you or something, then in order to find the generalized entropy, we need to take a cut of this null surface so that we then define the quantum fields on one side of this cut. We can then just think of it as taking an infinitesimal change of which cut we're taking. And that is a functional derivative of this quantity, the generalized entropy, with respect to this, null coordinate. So then, in order to try to extend these results to quantum situations, we proposed a conjecture that we call the quantum focusing conjecture. The idea is that maybe light rays still focus if you're interested not just in the area, but instead you're interested in taking a second derivative of the area plus the entropy of quantum fields on one side of it. So to write that mathematically, we just take a second functional derivative, and then we say this thing is always less than or equal to 0. The idea is that you can use this in place of the null energy condition to prove the same sorts of results you would have from the null energy condition, which suggests that you can't violate causality, but that there perhaps are still singularities. Now, of course, anytime we talk about full quantum gravity, that's always going to be a very speculative thing. We're just sort of bootstrapping our way to this by moving, instead of just talking about classical field theory, we can start talking about quantum field theory in curved space-time and start taking into account a small back reaction due to a quantum stress tensor. So, and then you can start thinking about Feynman diagrams of gravitons and so on. So any statements I say about, full-blown quantum gravity would necessarily be speculative. But what I can say is that as you begin to take into account quantum effects perturbatively, they do not seem to, these focusing results generalize in the way that I said. Now, so far, I stated this as a conjecture, and in general it is, but we have begun to prove it in several important situations. So if you consider this quantity, it's a second derivative of the generalized entropy, the area of a surface plus the entanglement entropy on one side. And in general, this has two types of terms. It has, in general, it's bilocal because you take two functional derivatives that could be at two different places on the null surface. But it also has a contact term piece a piece that's just proportional to delta function that's local. You can see that such a local thing would have to be there because part of this thing is just the area. And the area, the area piece is just local. And so any changes to the area piece are just purely geometrical. So what we did is we considered two cases where the second derivative, you could take this null surface and you could push forwards or cut either in two different places, or you could push it forwards in the same place. That corresponds to these two terms. In the first case, where you push it forwards in two different places, this sort of off-diagonal piece of this quantum focusing conjecture turns out to reduce to a property that's true that people can prove in information theory for all quantum systems. It's called strong subadditivity. It says the entropy of a system AB plus the entropy of a system BC is always greater than or equal to the entropy of the union plus the entropy of the intersection. So this part's just sort of automatically proven. But the more non-trivial thing is what if you take a second derivative that is along a single little pencil of these light rays, of this null surface. So it's most interesting to think about a case in which your surface, your null surface traveling at the speed of light is nearly stationary, where you just deform it a little bit with quantum fields, because then both the area piece and the entropy piece turn out to be the same order in your expansion parameter, which is g times h bar. So when you do this, we actually find a statement which is true, which would have to be true for non-gravitational theories, which we call the quantum null energy condition. So the statement is that in a quantum field theory, the null-null component of the stress tensor would actually be bounded below by a quantity related to the second derivative, the second functional derivative of the entropy of the system. You can see the relationship of this to the focusing that I talked about earlier, because if you use this linearized Ricciarduri equation, TVV is just proportional to the second derivative of the area. Move it to the other side, and you have the second derivative of this area plus entropy on one side that I was telling you about. But the interesting thing is we now have a statement that would have to be true even in an ordinary quantum field theory. Now it's something that we can check to see if it actually is true. So we checked it, and in certain cases, we've been able to prove it. If you just take any bosonic field theory, and so just take a free field theory or turn on some relevant couplings that have positive mass dimension that don't affect the physics in the ultraviolet, then we were able to prove that this holds in every single state of the theory. I should say, we call it the quantum null energy condition because the regular null energy condition would say that TVV is greater than or equal to 0, and now in quantum field theory, we've corrected that 0. It's neither stronger nor weaker than the regular null energy condition because this thing on the right-hand side could be either positive or negative. So it depends on the situation. When I say bosonic here, we didn't do the fermionic case, but that was only because we were too lazy to figure out where all the minus signs go. Presumably, it works in a similar way. We've also checked it for a class of field theories that are called holographic field theories, which uses the ADS-CFT duality. This relates a class of theories with a large number of matter fields that are strongly coupled to general relativity in the higher dimensional space-time. So this is a pretty amazing duality. I understand Dan Harlow talked to you about it a couple weeks ago. Jason and Stefan, and not me, proved that in one of these holographic field theories, which is dual to a general relativity space-time. If you assume the general relativity space-time that matter obeys the ordinary null energy condition, then in the corresponding dual quantum field theory, it obeys the quantum null energy condition. So this quantum focusing conjecture, it's a novel space-time thermodynamic principle. It's a lot like the generalized second law of black hole thermodynamics, and that unifies geometry with information theory. It suggests that maybe geometry is a sort of coarse graining of something that is really statistical and mechanical. But it's more local than black hole thermodynamics because this is a statement that would hold about every surface traveling at the speed of light, every null surface anywhere. It doesn't just have to be an event horizon or something like that. And it's useful for extending these GR theorems to more quantum situations and suggests that maybe these causality principles really can't be violated even with quantum effects. Now, in general, this is a conjecture, but in semi-classical situations where the quantum effects are a small perturbation, we succeed in reducing it to this quantum null energy condition, a lower bound on the null-null component of the stress tensor in terms of the entropy, and this is we've proven it in the cases I just mentioned. Now this is interesting because we started with a quantum gravity question and we ended up with an interesting partial theorem, partial conjecture that would apply to regular quantum field theories that maybe somebody who doesn't have any interest whatsoever in gravity would still be interested in studying. So it's interesting somehow quantum field theory knows that it might be coupled to gravity somehow, and it can be used to derive novel relations about the way that the energy fluxes and entropy fluxes in quantum field theory have to go together in some beautiful, consistent fashion. So that's everything I have to tell you. Right. So it's part of the issue with something like that. One is trying to find the goal is to find a sort of as local or as specific as possible an assumption that would rule these space-times out. Because a statement that no time machines are possible is a very global statement. You could not just look at an individual region of space-time to prove the non-existence of time machines, because it would involve different parts of the whole space-time sort of working together to produce this time machine. So it's sort of when you're playing these games about trying to prove theorem, of course you can assume whatever you want to and postulate as a fundamental principle. The question is just whether it's rich in terms of being able to derive interesting results, and whether it's likely to hold in the theories that we're actually interested in. So yeah, I mean, it's perhaps people should assume such things and just see what follows, but and sometimes they do in many of these theorems. But you also want to check that the assumption is in fact true.
All right, I'd like to end time. Singularity.